Hi everyone. Yeah, everyone can hear me, right? Yeah, cool. Nice to meet you. Thanks for having me. And thanks for the organizers for organizing this. Are we going to switch to my slides? Until we get this set up. Who here is from a science background? Raise your hand. And who's from a non-science background? Nice, 50-50. We have a nice mix. So for those who don't know, I actually started off as an art student before I switched to physics. So I can relate to both halves of this room. So yeah. Shout out to all my non-science people out there. yeah. So yeah.
Oh yeah.
Woo, okay, here we go. Hi everyone. My name is Ahlam. Today I'll be talking to you guys about how we get X-ray vision of supermassive black holes as scientists. Can people here see? Am I blocking your view? You guys are okay? Okay, cool. So let's get started. First I'll go through a roadmap of what I'm going to talk about today. So I'm going to first introduce myself and a bunch of the things that I work on. Then we'll talk about what black holes are for those who are not familiar with any of those concepts, so I'll walk you through those. Then we'll talk about how we study the evolution of supermassive black holes, which are the much bigger versions of normal black holes. And then I'll talk about how we can use X-ray satellites to study the evolution of these black holes. And then we'll go into what I like to call the magic of X-ray data, which is not so magical, but you'll see why. And then we'll summarize with the big picture and with any future applications of this work. So thanks for having me. So first I'll just quickly introduce myself. As Mori-san mentioned, I'm a PhD student at the UCL Space Science Lab in the UK. And I'm also in parallel the student PI of a CubeSat mission that I worked on during my bachelor's, and it was launched by the space agency, by the UAE Space Agency 2 years ago, so it's currently in orbit. And from the research aspect within my PhD, the first half of my PhD focused on supermassive black hole evolution, and that's what I'm going to talk to you guys about today. And the second half of my PhD, which is what I'm finishing up now, is focused on exoplanet detection and characterization. So if anyone's also interested in that, please feel free to have a chat with me about it. And some interests outside of academia, which I feel like helps me keep my sanity, are art, some outdoor sports, and I really enjoy doing science outreach, hence why I'm here. So yeah, if anyone's interested in any of those things, please feel free to also chat with me about those. And if you'd like to stay in touch with me, I put my email and my Instagram at the bottom, and I'll also put that in the final slide in case you miss it, so you can get it. Right, so let's get started. So first, I'll start by talking about what black holes are. To talk about what black holes are, we have to talk about where they come from. And I don't know if many of you know, but black holes come from dead stars. And so to explain why they come from dead stars, you have to talk about the lifetime of stars. So stars, like human beings, are born and then also die. So when you start forming a star, you have this stellar molecular cloud in space. There's a lot of material there. And eventually, over time, they clump together to form structures. And depending on how much material is there, you can either have a small star that's born or a large star. So we're going to follow the bottom half of this image because that's what leads us to black holes. So once you have a large star that's born, it ends up growing over its lifetime, eventually into what we call a red supergiant. And that's just a fancy word for saying it's a really old star. And it's grown past its age and very close to its death. So once it's an evolved old supergiant, past that point, it runs out of fuel to sustain itself. So it's almost like it doesn't have any more energy to keep itself going. So it's very close to its death. And by that point, a very big explosion is triggered, and that's called a supernova. And during the supernova event, a lot of the matter that used to be within the star gets blown away, and only the very heavier parts or more dense parts of the star remain, and that collapses on itself because the gravity of this explosion is so strong. And depending on what the initial mass of this red supergiant was, you either end up with something called a neutron star or a black hole. So I'm not going to focus on neutron stars today, but you can ask me about that after the talk if you're interested. But essentially, if you have a mass that's large enough, if your star is big enough, when this explosion happens, it collapses into a black hole. And that's how black holes are born. They're born from dying stars. So just to give you an idea of the scale, like what do I mean by having a large enough mass or collapsing under its own gravity? So let's compare the mass of a black hole to our sun. Imagine every point in this video is our sun. And imagine adding all of those suns together and piling them up and replicating them more and more and more and more. So imagine compressing all of these suns into a very small region of space. So you have
20 billion suns.
Yes, exactly. Imagine 20 billion suns in a region of space that's smaller than a football field. Can you imagine fitting 20 billion suns in that? That's insane, right? I mean, that's how massive black holes are. So I think a lot of times we don't grasp the numbers of this very well until we put them into context. So yeah, I hope that helps you kind of visualize the amount of gravity that we're dealing with here. So I think many people might know that black holes suck a lot of things in, and that nothing can escape a black hole, not even light. So if that's the case, how do we know they exist? How do we actually study something that we can't see, that nothing can escape? I mean, we can't even see the light coming from it. So can anyone guess from this video how we would detect a black hole if nothing can escape a black hole? Wild guesses. There are no wrong answers.
The light from what the energy is being pulled into can be observed disappearing.
Yes, exactly. That is exactly right. So what we see in this video is actually an invisible black hole in the middle where the black dot is. You can't see the black hole itself, but what you can see is a neighboring star. So there's a star that's very close by to the black hole, and the gravitational pull of the black hole is so strong that it's sucking up all this material from the star. But because of something called the conservation of angular momentum, this process is actually very slow. It takes about billions of years before the whole star is actually consumed by the black hole. Because the material can't just zoom past in and directly enter the black hole. It has to actually rotate around it slowly, and it spins faster and faster as you get closer to the center, after which it completely disappears. So this is what we observe as scientists. It's a more indirect way that we observe black holes, and that's how we know that they exist. Yeah, so just maybe a clearer schematic. This is a nearby star on the right that would be close to an active black hole. So not all black holes have stars near them. So there are actually many black holes that exist that we have not detected yet, just because we can't see anything close to it, so we can't see any light entering them. So the only ones we're aware of are the ones that have activity, which means they're actively sucking up material in. And so the material that spirals around the black hole before it disappears is called an accretion disk in astronomy, and the black hole is normally at the very center of that. So that's the general, yes?
When you say nearby star, how far is nearby? In general, like how far can it get before it's like escape? Like how far away can it pull in?
Yeah, I mean, it depends on the size of the black hole, actually, because...
What's like garden variety?
Well,
Sorry.
I think it would need to be... Well, let's try to talk about an astronomical unit. So 1 astronomical unit is the distance between Earth and Sun. So that's 1 AU. And it can go up to tens of AUs just to suck something in. So they don't actually have to be very close. But again, the gravitational pull of the black hole depends on its size, or I guess not, size is not the right word, the mass of the black hole. Yeah, if you have a really massive black hole, it can extend to very, very large distances, even across a whole galaxy. Actually, I'm going to talk about that in a bit, because we're dealing with supermassive black holes. But yeah, it can go across very large scale distances. Yeah. Oops. Sorry. Yeah. So yeah, now we'll switch gears and talk about the evolution of supermassive black holes. And supermassive black holes are just ultra-large versions of normal black holes. As you'll guess from the name, scientists are super creative with their labels. So supermassive black holes, to kind of understand why these are different, we have to look at the centers of galaxies. So actually, I don't know if you know, but we have many galaxies out there outside of the Milky Way, and almost all of them have been proven to have a supermassive black hole at the center. So supermassive black holes played a key role in how galaxies are formed. So any galaxies that are still active, or that are still evolving, or that still have stars that are forming, will have an active supermassive black hole. It plays a key role in star formation and in developing a galaxy over time. So these supermassive black holes grew by, again, gathering all this material, but instead of just one star, it's like material from an entire galaxy. So the structure is a little bit different. So if you look at a normal galaxy here, if you look at the very center of the galaxy, it's one of the most luminous regions of the galaxy. And this is kind of the structure that you look at. Remember I said we have a black hole and then we have a disk of material around it if we're just sucking up a star. But if you're in the middle of a galaxy, there's this extra layer of material and dust called the torus, and that surrounds the normal accretion disk. Just because there's just so much more material going on, and these are properties that make supermassive black holes different from normal stellar-sized black holes. And so if you zoom in here, the black region shows where the supermassive black hole would be, and then you'd have the accretion disk from the inner region. So that's the basic structure of what I'm studying, which are supermassive black holes.
How supermassive is that? Like, in terms of number, like what do you mean by supermassive?
It would be around, like what I showed in the video, like maybe 20 billion times the size of our sun.
The difference from like normal black holes you mentioned in the star, right? And this
Yes.
supermassive, how big is that?
So normal sized black holes would be around the mass of normal stars. And normal stars are closer, maybe tens of the times of our sun, maybe hundreds the time of our sun. But when you go to supermassive black holes, it's on the order of billions. So it's much larger. Yeah. Everything clear so far? Yeah. Cool. So now we know what we're going to study. We're going to target supermassive black holes. But how do we target their evolution? I mentioned that we're going to study their evolution over time. So the way scientists study the evolution of supermassive black holes is by tracking redshift. Now, what do I mean by redshift? Redshift is just a fancy word of saying how far away something is from us, from the Milky Way, from our reference frame on Earth. And so the basic thing I want you to keep in mind is the relation between distance and redshift. So the further away a galaxy is that we're observing, the higher the redshift will be. It's just a measure of how far away a galaxy is. And why do we say it has a high redshift? It's because the further away something is, the light that reaches Earth takes a very long time. So actually, it's altered over time and it stretches out because it has to pass through a large region of space. And so we call this, or we measure this by looking at redshift, because if you look at the visible spectrum, the spectrum is just what you see with your eyes, and focus on this thin black line. If there's a nearby galaxy, the original black line would be close to maybe the green part of the spectrum, and you see like a normal wave. The wave is just a wave of light. And then if you look at the middle part, the black line is shifted more towards the orange region because this galaxy is a bit further away. And the wave looks a bit more stretched out, so because it took light a longer time to reach us. So it's modified by the time we detect it. And then you have really, really distant galaxies where the light is shifted all the way to the red. So redshift kind of gives you an idea on how close to the red side of the spectrum the light is, or how much it's stretching towards the red side of the spectrum. So yeah, that's what I want you to keep in mind. So the higher the redshift, the further away something is, and the more modified the light is by the time it reaches us. Sorry. Okay, so now we talked about redshift, and we talked about supermassive black holes, and we talked about wanting to track their evolution. So how do we tie these things together, and how do scientists actually apply this in our real everyday research? We do this by constructing something called a luminosity function. This is a fancy word for just saying we're going to count all the AGN, all the number of supermassive black holes that we see at all redshifts, at all distances. So that's essentially what this plot is showing. And we're going to measure the intensity of the light that we're seeing from all of these supermassive black holes. So essentially, we're just counting the number. So AGN is active galactic nuclei, I forgot to mention. It just means it's the active nuclear region of a galaxy where the supermassive black hole is. So if I say AGN, I'm talking about the supermassive black hole. So we interchange these words. And we're measuring their luminosity. Luminosity is just how intense the light is that we're seeing from these galaxies. And we want to see how they change across different redshifts. So are the very distant galaxies, do they have different properties? Are their numbers different? Is their brightness different over time? And how do they change as they come closer to the present? So that's really what we're tracking here. But to do this, we need a lot of data because we need to be able to track a huge number of supermassive black holes to be able to understand maybe with more certainty how they evolve with time. So that brings us to the current limitations of that. So we're very limited in how we can acquire data because we can observe from Earth, telescopes from Earth, or we can send satellites to space, but we're still in the Milky Way. I mean, we can't send a satellite all the way to the supermassive black hole and observe exactly right in front of us what's happening there. We're very limited by the fact that we're stuck here on Earth. All our satellites are more or less within the Milky Way. We can't launch anything past that. So that poses problems when you actually collect data about supermassive black holes from other galaxies within the universe. So imagine you have a galaxy at redshift 0. So 0 means it's right next to us, the light isn't really being shifted, right? Remember, higher redshift means it's further away. If you observe this galaxy in a given energy band, let's say between 2000 and 8000 eV. eV is just electron volts, it's a way we measure X-ray energy. Okay? We would be observing the exact same energy if it was close by. It would reflect the true reality. So that brings us to reference frames. We have an observer reference frame, which is us. It's what I'm able to observe from my limited location. And then we have the rest frame, which is the true internal state of the supermassive black hole without any observational biases. It's as if you were standing right in front of the black hole if you were able to observe it directly, and if you weren't limited by location. So what we're trying to do as scientists is to get as close as possible to this rest frame. How do we trace the true internal state of these supermassive black holes when they're very far away? So that brings us to the second case. Imagine a very distant galaxy at a higher redshift, let's say at redshift 2. If I'm taking an observation in the same energy band, let's say 2000 to 8000, by the time the light has reached us towards Earth from this very distant galaxy, even if the true internal energy of this supermassive black hole is 2000 to 8000, what we're actually receiving is very different. Remember, light gets stretched out, and so what we're seeing is something around 700 to 3000 electron volts. It's very different than what we're actually observing. And the way scientists try to account for this is by modeling it. We have some physics laws, we have some theoretical models. We try to predict, kind of work forwards after collecting the data, how to actually account for this and how to modify all the light that we receive and fix it by guessing what the internal state of the supermassive black hole was when it's very far away. But again, how do we know we're right? How do we know our models are correct? How do we know our assumptions are correct? So are we truly probing the true internal state of these supermassive black holes when they're at higher redshift? And so that brings us to what I work on, or what I worked on during the first half of my PhD. Remember, my goal was to investigate how supermassive black holes form and how they evolve with time. And again, if we want to look at how they evolve with time, we have to look at galaxies that are not just close to us, but that are also very distant at higher redshifts. And so the way I do this is to actually construct these luminosity functions where we count the number of AGN at different redshifts, but we do it in different energy bands that match the redshift that they're at. So in bigger or smaller terms, most people just pick one energy band and they observe everything at the same energy band. But that doesn't reflect the true internal state of these supermassive black holes when they're at higher redshift. So I developed a new method with my supervisor back in the UK to actually construct these luminosity functions so that they reflect the true luminosity that's coming from the AGN, and then we eliminate the need to model or guess how they evolved with time. So, why did I choose to work with X-ray data to do this? Remember, we're looking at the center of a very active galaxy. And galaxies emit light in all types of wavelengths. What does this mean? So imagine I take the optical waveband. The optical just means it's visible light. It's what you can see with your naked eye. It's the fact that I can see you here and you can see me. It's the fact that we can observe stars in the night sky when you look up. That's visible light, and that's what our eyes are able to pick up. So if you look at the bottom left of this image, it shows you a picture of the same galaxy, but only in the visible light. And you can see so many stars there. And stars are actually very luminous, so they produce a lot of noise. They contaminate the light that's coming from the supermassive black hole. But I just want to look at the supermassive black hole. I just want the light from the supermassive black hole. So how do I do that? The best analogy for this is, imagine you're going to a doctor and you've broken your arm, and they want to inspect your bones. You can't take a normal picture of a human body to be able to see their bones. You're blocked by muscles, you're blocked by skin. It's not something our eyes can see. So what do? We take an X-ray scan, and that helps us isolate just the bones in your body. And in a similar way, if we want to isolate the activity that's coming just from the supermassive black hole, we develop X-ray vision of these active galactic nuclei. And so in the bottom part, in the middle bottom part of this image, it shows you an X-ray image of the same galaxy without any star contamination and just focused at the central region where the supermassive black hole is. So that's why I'm targeting X-rays in this case. So if I'm going to use X-ray data, I need to use X-ray satellites. And in my case, there are many X-ray satellites, but for my research, I use the XMM Newton satellite, which is a joint mission by NASA, the American Space Agency, and ESA, the European Space Agency. Sorry. Lots of water. Okay. So, how do we collect X-ray data? If you took a normal camera and tried to capture an X-ray image, you would see nothing. Because X-ray particles are very high in energy, and they would just penetrate through all the equipment. So how do we study these X-ray particles in space? We have to develop special and very long mirrors. And what these mirrors do is they just graze the X-ray particles as they pass through. And they slowly redirect their direction until they reach the point where the X-ray camera is. So it collects all the light, redirects it very slowly over a long mirror until it reaches one focal point, where the X-ray camera is. So this is how we take X-ray data from space. You need very long telescopes with long mirrors. So just to show you how this is done in the XMM-Newton satellite, in this video you'll see light entering the satellite, and you'll see there's a long region here in the middle. So it'll show you now how the light gets redirected through 3 sets of mirrors. So the XMM-Newton satellite has 3 X-ray cameras, so you need mirrors for each camera to focus the light towards the camera. And that's what you're seeing in this video here. It's allocating or collecting all this light until it reaches a focus point where the X-ray camera is. And that's a real-life picture of what the cameras look like before they were launched in space. So yeah. Now imagine we took all this X-ray data and we want to take an X-ray image, and after doing some magic, this is the kind of image that we would see. So that's an X-ray image of a region of space, and there's a lot of different objects in this, which include supermassive black holes, it includes galaxies, and this is all in the X-ray. So this is actually one of the images I used in my research, and I'm just showing you the end product of what it looks like after we use this X-ray data. But what is this magic that I'm talking about? And that's what we're going to get into for the last part of our talk. When I talk about the magic of X-ray data, what I really am talking about is how difficult it is to work with X-ray data. So just to give you a quick outline of how you would start to approach this, first you have to pick an X-ray satellite. In my case, I picked XMM-Newton, and it has 3 X-ray cameras. And then you have to choose a survey. Remember, we need a lot of data to study the evolution of supermassive black holes. So I have to collect an entire survey of all these X-ray sources. So once I have that, we want to produce X-ray images. My satellite has 3 X-ray cameras, so we produce 3 X-ray images. But I want to collect all the information from those images, so what I do is I have to sum up all those images together, add up all the light that I get, and develop this one final X-ray snapshot of this region in the sky that I'm looking at. And then with some fancy work, we run a source detection chain. So we try to detect all the sources that are available in this image, and we try to measure how much light is coming from these. So that's all that it means. And then once we have that, we have a final X-ray source list with the location of the source and how bright it is. And once we have that, then we can start tracking the evolution of these sources over time. So how would someone start working with X-ray data? So actually, there are 2 sides of X-ray, or satellites in general. There are 2 sides of working with space missions. There are teams that work on the data collection, and they work on processing the data. And then there are scientists like me who want to use the data for actual science. So the scientists that work under the XMM-Newton satellite upload all the data on a public archive. I mean, any of you can go on this website and access it. It's really nice, and you can just play around with the data if you really wanted to. And you can filter the type of data that you want based on different criteria that I list here. These are just some of them. And so there are different ways to navigate this. So this is how I would start accessing my data. I just download the data that I want from this public archive. The first thing that I would do is look at background flares. So X-ray data is not always clean. Sometimes we have events that are contaminating our data. This can be things like, let's say a charged particle shoots through my instrument and causes this flare in the light curve. So what you see here is a light curve, which just tells you how much X-ray light we see over time. So on the x-axis is time, on the y-axis is just the number of particles over time. And so, as you can see, we have the good data at the bottom, and we have this background flare from an event that we don't want, and it's contaminating our data. So the first thing to do is to filter these out. So we have to apply this threshold and filter out all these background flares. And once we do that, we can maybe trust our data better. Now this looks like a very clean example. You can very clearly separate the background flare from the good data. But what happens when it's not so clear? In that case, you have things like this. And sometimes it's not clear where you should draw this line. And in reality, X-ray data actually is not that much. So even within a long period of time, you're only getting a few X-ray particles. So it's not the same as visible light. So in reality, we're actually compromising between how much background we're allowing into our data set, or I guess how much contamination we can afford to have in our data sets based on how much the exposure time is.
So, what is normally the source of the flare?
It can be like a charged particle from space, so maybe a cosmic ray, or it could be flares from other sources. Sometimes it's just data systematics as well. So it's not always clear what the contamination is. But you can clearly see them because it's very different from the baseline level when you're taking the observation. So actually, depending on your science case, if people specifically want to focus on the background flares, maybe they won't filter them out. But for my case, I don't want to study the background flares. They're ruining my data. I want to get the precise light that we're getting from supermassive black holes. And so I want to make sure that when I do these measurements, they're correct and they're not being modified by any external source. So I want to filter them out as best as possible, while also making use of as much data as I can for each source. So in reality, we're like making a compromise between these two. And the way you make this compromise depends on your science goal. So for my science goal, this is maybe what I can compromise on, but maybe for someone else with a different science goal, they would treat their X-ray data very differently. So it depends on your science goals in the end. So I mentioned that I'm using 3 cameras from XMM Newton. So this is actually what you would see from the 3 different cameras if you took an X-ray snapshot. So again, this is from my own research. So on the left is an image from the M1 camera, in the middle from an M2 camera, and on the right from the PN camera. And remember I mentioned we're going to sum up all these images together to make use of all the data that we can get. And that gives us our final X-ray image. Maybe it doesn't look as nice as those Hubble images that you guys see. But again, give me some credit. We get very little X-ray count in X-ray astronomy. So this is really, really good when you work with X-ray data. But there's a catch. What happens when you have differences between the cameras? The cameras are actually not identical. You saw the shapes of the images are actually very different. And sometimes you get a background flare in one camera, but not the other. So what do you do in that case? As an example here, in the blue light curve that you see, that's from the M1 camera, you get a very large background flare. And from the M2 camera, you get almost no background at all. So in those cases, you have to actually be very careful. You have to process these images separately. You have to remove the background sources separately for each camera before you combine them together in this final image. You can't just do it at the end after you've combined it, because then it becomes much more difficult to place the threshold. So that's when...
I'm sorry.
Yeah.
Is it possible that you use the data with no flare to calibrate the data with flare?
Actually, so these are from the same exact observation, so it doesn't require any calibration. So this is the same observation, same time, same telescope, but we have 3 cameras, so they're simultaneously taking data at the same time. So the only thing I would do here is to apply different thresholds. So for example, here, so here, let's say I put a line here for a threshold. Normally, if the cameras are similar or the activity is similar, I would just put 1 threshold for all of them and quickly finish the data processing. But you have to be careful. You can't just assume all of them will have the same level of background flares. And so that's why in that case, even when you deal with a large data set, it takes a lot of time, but you have to actually inspect your light curves and make sure that you're filtering out background flares that are there. So yeah. Then, yes, that's correct. So now I mentioned that I have a lot of data, and okay. I mentioned that I have a lot of data, and I wrote maybe a program that helps me process this data. Otherwise, it would take a very long time if I did it by hand, one by one. The issue is that, well, one thing that I was discovering anyway through my own journey with X-ray data is that for the same event and the same exact camera, you can get very different images. So for example, if you look at the 3 images here, the one in pink and blue and green are all from the M1 camera, but they don't look the same. And it's because they have different frame modes. The frame mode just means whether the full camera is exposed during the observation or part of it is blocked. So this is why you see these black squares in some of them, because part of the camera is actually blocked during the observation. There are different reasons of why they do this, but for my specific science case, I want all the data. I want as much of it as possible. So what you can do in this case is you can maybe just choose the full frame image, which just looks at all of it. But also I want to make use of this extra data that I have. So maybe I can also combine them. So you have to kind of make a choice in that case of how you deal with this, again, depending on your science case. And this is not something I was aware of when I first started my research. So I ran into a lot of issues with my source detection chain. So unfortunately, it's not a very automated process, and you do have to be careful when you deal with these things. The other thing is sometimes you get missing data, which didn't make sense to me at first, but I found out later that XMM Newton has scheduled observations, which are denoted by S. So if you look at the second column, the first letter is either an S or a U. S means it's scheduled, which means it was planned. They planned to observe this part of the sky at this specific time for this amount of exposure time. But sometimes things don't always go the way you plan. Maybe the telescope had issues. They have to recalibrate it. Maybe it shut down. Maybe some event passed through and they have to stop observations and repeat them again. But when they stop observations and repeat them again, they actually publish them as separate data sets. One is scheduled and one is unscheduled. And I had no idea this even existed when I first started my research. So I was only taking the scheduled observations. But the issue is, many times the unscheduled observations are much longer, and the actual real data is in the unscheduled observation. So I was actually missing a big chunk of data when I was starting out. So just to give you an idea what this looks like, there are 2 light curves here. On the left is a scheduled data set for the same observation, and on the right is an unscheduled data set. I think you can just look by eye the amount of difference that you see between the scheduled and unscheduled one. It's not always this case, but sometimes you get cases where the unscheduled data is much more. So the one on the left is only 10 minutes long. The one on the right is almost 10 hours. Can you imagine dealing with a data set that's only 10 minutes long versus one that's 10 hours? So I was missing 10 hours of data for this data set, and it took months to debug this, actually. So research is like this. Sometimes you don't realize stuff like this happens, and you have to get to the bottom of why you're getting issues in your analysis. And then you have cases where you have extra data, which is the opposite problem. So sometimes you have different observations, but they're looking at the same target source. So in that case, how do you know which one to choose? So there are 2 options here in this case. You can just choose the one with the longer exposure time. So in this case, the duration on the last column shows you the amount of time in seconds for each observation. So this is around 70,000 seconds, and this is around 20,000 seconds. So if you were going to take the one with the largest amount of exposure time, you'd probably take the top one and just discard the bottom one. But again, we don't get that much extra data, so I want to make use of all the data we can get. So what you can do is actually merge them together and make use of all the data that you can possibly get for each target that you're trying to observe. But then that also causes other issues. Because observations are separate, it means they were taken at different times, it means they were taken in different conditions. So the pointing of the telescope won't always be aligned. So if you'll see when I stack the images together, the lines of the detector edges don't align very well. And so sometimes that can cause part of the sources from one image to be blocked off, while part of the other image to show. So this is not always the ideal situation. So again, it depends on your science case, and this is generally why people don't merge observations together. But the way I deal with it is that I apply a mask on top of the blank regions so that they don't block any light from one image or the other. So that's one of the ways you can deal with this. Cool. Now we'll go to the final best part of X-ray data, which I like to call the Satan of data, and these are spurious sources. This is what probably took the longest to work on during this research project. And spurious sources can come from different places. It can be contamination from external events or things like cluster sources. Cluster sources are basically star clusters. It means there's a very large amount of stars like squashed together very far away. So your telescope can't actually resolve them, each star separately. So it just looks like one very bright star. But not just that, the light from that is so strong, because star clusters are very bright, that they contaminate all the data around it. So actually, you can't really trust the light that's coming from nearby sources, because the light from the cluster itself is adding more light than what's actually there. So this is a problem, and we don't want to deal with sources like that. They're not very reliable. Other sources can just be data artifacts or systemic effects. Sometimes when you write an automated program to pick up your sources, it's not perfect, and stuff like this happens. The point is, they're sneaking into my source lists, and I don't want them there. So we have to find a way to remove them. So I mentioned cluster sources. This is an example of a cluster source in an X-ray image. You'll see these normal X-ray sources look fine, they're well resolved, and then there's this big X-ray emitting cluster in the middle, which is contaminating the light of all the surrounding objects. So I can't trust, let's say, this source here or that source there, because it's being contaminated by the cluster. And the number of stars that are being picked up are much larger because the program gets confused. So what we want to do is apply a mask and block it off. And so this is what you would do in this case. And that would help you fix the problem. So you would avoid picking up any sources that are close to cluster regions. For my research anyway, because I'm not targeting cluster sources. And then you deal with fake sources, which was a brain scratcher for me, because sometimes I would inspect sources that look weird, and then when I look at the image, so the circles show what my program picks up as a real source. But when you look at the image, nothing's there. I mean, they're either at the edge of the detector, or they look like they're maybe picking up a little bit of background. It doesn't look like a real source is there. So how does this happen? Like, why do we have these fake sources, and why are they being picked up by my program? So that was another problem that I encountered. And so this is where I apply data exorcism. We want to remove all these satanic sources from my data sets. And so examples of what these look like is, imagine these are all my sources, and then you have isolated case sources like these, which I put little devil horns around so you guys can see better. And the ways we can filter those out is we apply different data cuts to make sure they're not included. Some of the things we can look at are how strong the signal is compared to the background. If the signal is very close to the background level, it means it's not very reliable. So we remove things like that. And one of the things we can also do is look at the likelihood. The likelihood tells you how likely it is, based on a probability distribution, how likely it is that this source is real, or how likely it is that it's a fake source. So stuff that have a low likelihood or a low probability of being a real source, we scrap those. And the problem is those ones have actually very high fluxes. Flux is just another way of looking at the light intensity of these sources. So imagine thinking you have a very bright source that could be a supermassive black hole, but it's not a very reliable measurement because either the signal's too close to the background, or it has a low probability because it's maybe too close to the detector edge, or it's in a region that's not very good. So we want to remove all these out. So as an example, some of the sources that I remove are circled in green there. Once we apply this magic exorcism, you get a very clean data set, and we can trust the data in our source list much better. And so now I've reached the final end of actually working with X-ray data, and I think you can appreciate now what I mean. The magic of X-ray data really just means X-ray data is very difficult to work with and has a lot of complications when you actually get down to it. So now we'll talk about the big picture, and we're almost done, I promise. So I talked about how we want to produce luminosity functions of supermassive black holes, and we want to use X-rays to do that. But first I mentioned that these luminosity functions change a lot based on the redshift of these sources, so how far away these sources are from us, or from where we're measuring them from. And so this causes issues when you observe everything in one energy band. So my method was to develop a new approach to try to deal with that problem. And I use XMM Newton data for my X-ray sample, and it's a large survey, and I just showed you how we handle this X-ray data. And I don't have so much time to go into the new luminosity function that I developed, but if you're interested, these are the details to my paper. Please check it out or have a chat with me about it. But we've shown that this new method works, and it describes the data much better at higher redshift. And so future work would be to extend this method to a much larger data set. Maybe we could use X-ray data from other satellites, not just XMM Newton. So the thing to highlight is this is more of a proof of concept. We only use one survey from XMM Newton, and it's just to show that this method works, and it can work very well. And we want it to be hopefully the leading approach in making luminosity functions in the future of X-ray data of supermassive black holes. So that's about it. Thank you so much for staying with me through the talk. I hope it wasn't too confusing, and I'll take any questions now if you guys have any.
Sorry, I'm a bit confused about, you said that you were going to make a new method or kind of exploring the luminosity function of the agents, but
Yes.
you don't show any in your slides.
No, I didn't have time to go through the luminosity functions, so we only have an hour. I wanted to go through the X-ray processing more, but I'm happy to talk about it a bit more if you want. Do you have any specific questions about that?
Not really.
Okay.
But I have one nice question about
Yeah.
X-ray.
Yeah, sure.
One basic,
Yeah.
rather nice.
Yeah.
You said earlier that for supermassive galaxies, I mean far away galaxies,
Yeah.
You have the redshift.
Yes.
And for the farthest galaxies, like you have a very big redshift.
Yes.
Like, the wavelength is just very red.
Yes.
But you can actually observe the X-ray, which is like the blue part of the spectrum.
No, the blue and red parts are just from, it's just to show you an example of how the Doppler light shifts. So it's actually the visible spectrum. But the it's just to give you an idea that light stretches, or the energy stretches by the time it reaches you. So the red and blueness comes from when you take a snapshot of a galaxy with an optical camera, like a visible light camera. The ones that are redder are far further away, and the ones that appear to have a bluer color are closer to us. But that's determined by the visible image, not the X-rays. Yeah.
Thank you.
Yeah. Yes.
So I had, thanks for the talk.
No worries.
Two naive questions, I guess.
No worries.
So you mentioned that black holes are at the end of the evolutionary track, and when something starts off as say 10 solar masses,
Yeah.
like a star,
Yeah.
how does it where does the the other 19 billion whatever solar mass come from to form?
Yes, good question. So as a star develops through time, it has fuel from different elements. So you start off with a hydrogen gas layer, and those elements fuse together to create heavier elements with time. So eventually, you have kind of like imagine an onion, and the core of an onion has the heaviest part, and as you go out, you get to lighter and lighter elements. So the surface part of the star would be maybe hydrogen or helium, they're the lightest elements in the periodic table. But as you go further and further in, you eventually reach maybe an iron core. And iron can't fuse anymore to make something heavier. So then the gravity from that collapses in on itself. So over time, you just produce heavier and heavier elements. And because you're condensing so much of it, after the supernova, you're condensing so much of it into a very small region of space and it collapses on itself, that's why that happens.
So it comes from the conservation of energy somehow?
Yeah.
I see. And I guess another question is, does a black hole evolve into something else after? Or is it just at the very end of the evolutionary tree?
Not that we know of. So black holes start off being very active. So as soon as they're formed, maybe it's a very turbulent environment. Maybe they're sucking in a lot of material from neighboring stars or material. Or maybe they're even merging with other black holes or other galaxies. And that's where gravitational waves get detected. If you have very strong black holes or neutron stars colliding with each other. But beyond that, eventually when things get settled down, black holes just kind of chill and they don't do much. And we call those the quiescent state. So that's basically the calm, non-active state of a black hole.
So eventually everything in the universe will be black holes, neutron stars, or vice versa?
Whoa, it'll take a very long time. But not everything, because sometimes, again, if it's a very small star, it'll eventually lead to maybe a white dwarf planet. But if it's not close enough to a black hole, it won't be sucked in. It'll just exist on its own. So yeah, they drive a lot of galaxy formation in different parts of a galaxy. They're not the only. It's not the only end result of things in space, but they influence a lot of things nearby them. Yeah.
Excellent.
Yeah. Other questions?
Yeah, sorry.
Yeah.
So for the supermassive black holes, they're at the center of galaxies, and I'm just wondering, I suppose it'd be hard to observe them in other settings because they have to be active in order to view them. But I was just wondering if there's any supermassive black holes that have been observed that are not AGNs, not the center of a galaxy, like they're. Yeah.
Like if they're very massive but not located at the center?
Yeah.
That's a good question. I'm actually not sure.
Okay.
I'm not sure of the answer. But I think the way supermassive black holes are categorized, they're the ones at the centers of massive galaxies. But there are black holes that are even more massive than supermassive black holes.
Okay.
But I don't know if they would also be located at the centers of massive galaxies or somewhere else. I don't have that answer for you.
What's the one bigger than a supermassive black hole then?
You can go maybe 3 levels up.
Oh wow.
Yeah.
Is there like a name or a term?
Yes. I think one is ultramassive.
Okay.
And then, again, scientists are not very creative with names.
Thank you.
Yeah. If you're interested, there's actually a very cool video on how these black holes form. It's by a YouTube channel called Kurzgesagt.
Okay.
Kurzgesagt, I think. I don't know, I'm spelling it wrong, but Kurzgesagt. Can someone look this up?
I think I found it.
Yeah. So they do really cool videos with really nice visuals of black holes. So if you're interested, and they also show the entire spectrum from small stellar-sized black holes all the way to the largest sized black hole that you'll ever see. So maybe check those out. They're super, super interesting and very, very easy to understand, even if you don't come from a science background.
Thank you.
Yeah. Welcome. Yes?
I have a very
Wait, sorry, the person behind you.
Not a question, but just want to say I like your font style.
Thank you. This is a free template. Anyone can use it. I just Googled it, so yeah. If anyone wants to give a pretty space presentation, anyone can use this template. Thank you. Yes? You had a question?
So I know your discussion was to make new luminosity equations and everything.
Yeah.
So is the end goal of that to be able to shift everybody from using the redshift to using X-ray?
Yeah, I mean, redshift exists, so we're not changing that, but we're changing the energy bands that we're observing these black holes in. So instead of observing everything, regardless of how close or far away it is, in one energy band, we actually vary the energy band that we observe these supermassive black holes in, because we expect, based on the redshift, how much the light should have been altered by the time it reaches us, and what this true energy, internal state of the energy should be by the time we detect it in our telescope.
As a follow-up to that, like,
Yes.
what does that actually get you from a physics understanding standpoint? Like, what is being able to better calculate that? What does that result in?
Yeah,
for-
so that helps us see the true internal state of the light coming from an EGN. So instead of, so normally what scientists do is they observe everything in one energy band, and then they try to model how it changes with time. And so that modeling is, well, we can't say for sure if it's correct or not. So instead of trying to model for it after, basically dealing with the problem after you've created it, taking more preventative measures to actually observe it in the correct energy band, where we eliminate the need to model its evolution. By the time the light reaches us, we're observing it as it's supposed to be. It's just harder to do because there's a lot of X-ray data, and you have to cater the energy band you process your data in for each type of source. So it takes a long time, which is why people don't do this. But it's a more accurate method.
Okay. Can I just
Yeah.
seek a bit of clarification on that?
Yeah,
so
sure.
do you mean, regardless of the distance or how far away it is, we can work out a way to observe black holes, supermassive black holes, more accurately as they predicting how they are currently,
Yeah.
without having, like, I guess, fuzziness created by the fact that we're sort of making a little bit of guessing based on
Yes.
the redshift and things
Yes,
like that.
yes,
Okay,
exactly.
okay,
Because
okay.
energy is just, again, so energy, flux, luminosity, they're all words, fancy words for the light that we're seeing.
Right.
And the light that travels to get to us.
Yeah.
So we want to make sure we're targeting the right
Mm.
energy band, the right wavelength of light
Right.
when we're observing these.
So that might allow then, like, better prediction of how black holes work and how
Yes.
galaxy formation happens.
Yes,
and,
yes.
Okay.
Because let's say you make assumptions and your model is wrong about how it evolves, you're actually predicting the wrong luminosity that's coming from these supermassive black holes. So you might think, oh, at this redshift there are tens of thousands of very bright AGN, but maybe that's not true, and you didn't account for that very well. So it just gives you a better idea of how luminous they are and how that changes over time.
Thank you.
Okay, one or two questions?
Yeah. Yeah.
So you had some unscheduled observation, right?
Yes.
Versus scheduled observation.
Yes.
So it looks like the unscheduled ones at 10 hours or something, right?
Yeah.
So it has more noise.
Yeah.
So how does one come up with the threshold for, a 10-hour observation versus
Yeah.
something that was 10 minutes, right?
Well, you try to see where the baseline is of your good data, but again, sometimes it's not very clear, and you have to actually visually inspect it. Unfortunately, there's no automated way to do this, so I have to visually inspect every single light curve and make a best case decision on where to apply the threshold. Again, I could cut it out to a very, very low level, but I'm then losing a lot of data. So you have to kind of think about, based on what the noise level is, how much you're willing to compromise.
So it's just more or less visual inspection is the baseline.
Yes.
Really.
Yes. Someone else had the... There was someone here. Yeah.
For the cameras, why did they sometimes use like an extended full frame, so got a lot of data, and sometimes
Yes.
just a small frame?
It depends on what the goal of the observation is. Sometimes you want to isolate only the target in the middle, and you don't really care about the surrounding objects. So sometimes you block out the light around the target that you want, and that helps you focus the light that's only coming from the target. So sometimes they do things like that, and sometimes they calibrate their cameras for different reasons. So it depends on the goal of the observation, essentially. But for my science goals, I wanted the full frame image because I want to get as many X-ray sources as possible to track how many of them are supermassive black holes. But if you're just targeting like one source, because some people only target one source and they study that in a large amount of detail. So maybe they have different science goals, and then you would need different frame modes for that.
Did you use that large amount of detail somehow? Like, did you add it to the white picture?
I didn't. So the extra details that you could do is using the spectra. So there are actually, other than the 3 X-ray cameras, there are other instruments on the XMM Newton satellite, and those all go hand in hand. All these observations are taken at the same time. There's something called the optical monitor, which takes an image in the visible light in case you want to compare it to the X-rays. And then there's the actual spectrum of the stars. So it looks at what different elements you see in the spectrum of the stars. So those would be the extra information or the different side of X-ray data that you can use. But I don't make use of that when I'm doing luminosity functions. From luminosity functions, all I need is the light intensity of these X-ray sources.
Thank you.
Okay.
Okay, so the last question.
My understanding is that at the center of a black hole is something we call singularity. And my understanding as of now is that the singularity is like an infinitesimally small point, maybe like the edge of a knife.
Yeah.
But at the start of the presentation you mentioned that supermassive black holes are formed by condensing 20 billion solar masses into the size of a football field.
Well, less than that, but yes.
So
yeah.
Is a singularity not actually a point, but it's a point from the perspective of how big a supermassive black hole is, and maybe about the size of a football field? Or?
Well, singularities are complicated because truly, I mean, the easy answer is yes, there's a singularity point. But actually, singularity points are non-physical because the reason we think there's a singularity is because of maths. The maths doesn't add up and it leads to a solution that's basically infinite. So the singularity point reflects an infinite amount of space condensed into a single point, which doesn't really make sense physically. So it's actually a big gap in black hole research. We're trying to understand what this is or how it even works, but it's very difficult to study it because beyond the event horizon, which is this little hoop that's around the singularity point, once something enters that, you can't get any information out of it. So it's actually very difficult to know what happens beyond that, or what even the singularity is. So actually this is a big question in science still today. It's not something I can give you a clear answer on. But how big this radius is, or this hoop around the singularity point, as we call it, depends on the mass of the black hole. If it's a very large... Yes, exactly. So you'll have a larger radius for something that's more massive. Yeah.
And also when you mentioned football fields, did you mean soccer fields or American football?
There's no such thing as American football, sorry guys. I'm kidding, I'm just trying to be controversial. Where I grew up, football is just soccer. We don't have a different word for it. So a soccer field, to answer your question. yeah. Sorry guys, no offense to any Americans here. I was just joking. yeah.
Okay, so thank you very much.
Yeah, thank you so much, everyone. Yes, it should work. We just have to point it out. Yes.
Thank you so much. And today we see several new faces. Thank you so much for coming. So I will present me introduce what Space Cafe Tokyo is. So Space Cafe Tokyo is usually monthly event. So we have this kind of event every month. In this venue, we are starting 2019. Maybe, so it's more than 5 years right now. So always we are having our event. Circular track. Yeah. Push the. Yeah. So we are always having this event in this venue called Good Heavens British Bar. run by Hisako-san and staffs.
Oh, there you
Yeah, thank you so much. So they also have a social media accounts, so please follow them. And if you're, by the way, can you stay here a little bit longer?
Yeah, I'm
okay.
here for
So
a
she
while.
will be here. So if you have further questions or just want to chatting with her, please find her. And if you stay here, I will recommend you to order more food and drinks if you want. So they also have in this venue there are several interesting events. And actually tonight from 1 a.m. there is a soccer game. So if you're a football fan, just stay here until 1 a.m. And also they have charity quiz night on July 7th, and also there are some music live on 21st and 24th. If you're interested, please follow their social media account. And we have our sister event called Nerd Night. Nerd Night is event held in Kawasaki World Peace Theater. So it's very similar, but they are not focusing on just space, but anything nerd kind of things. So actually their event is tomorrow. Tomorrow at maybe 8 p.m. Probably, 8 p.m. So that they have two speakers. It seems the next one is about AI and cardio science. So if you're interested, please also follow their social media account. And also I want to introduce one of the science blog. It's Ain't Magic. It's run by, the QR code is cut, but you can find with this It Ain't Magic on social media. So it is science blog run by Riken. Riken is a Japanese, one of the science institute. So if you're interested in, just follow them. So actually our next event is not yet decided, but probably mid-July, mid or late July or early August, I think. So we will advertise our event later. So please follow our social media account for stay tuned for the next event. So this is our social media account, and we also have a YouTube channel to upload our past talk event video. So if you're interested in, please just search Space Tokyo Space Cafe on YouTube. So this is Space Cafe Tokyo team. So Ken is there, giving the door, and I'm Mayuko. Here. So Serena is absent today, and Case is our photographer. Yeah. So thank you so much for coming. This is ありがとうございます。